make an announcement. So apparently there's a problem with the heating in the room. So even though we might not feel it right now, the room will likely be much colder tomorrow morning. So it might be a good idea to come prepared for lower temperatures in the room when we start our second summer morning. Okay, so we'll start our last session of today, and talk will be given by Dave Smith. Talk will be about linear evolution equation on the half line with the related boundary conditions.
Thanks very much, and thanks very much to the organizers for the opportunity to speak. So I will present some results. Well, eventually I'll present some results from a paper that just appeared on the archive a week ago, joint with a current undergraduate student of mine, To Wei Yang. He'll be applying for graduate school now. So this is the problem that we're going to look at. It's a problem on the half line. We're looking at a problem of arbitrary spatial order. Although, just to simplify notation a bit, I'll assume that there's only one spatial term in the PDE. It's a linear problem. We have an initial condition, of course, and then we have some boundary conditions. But what makes this interesting is that these boundary conditions are allowed to depend on time, not just in the inhomogeneity, but actually the boundary forms themselves depend on time. Okay? And then this is just to make sure that the Cauchy problem is well posed and we've got the right number of boundary conditions. We don't need to worry too much about this. We just say if it's a problem of order n, then there's about half n boundary conditions is the correct number. Well, most of the talk I won't talk about that problem. I'll talk about the example problem, which is for the heat equation when we have this dynamic Robin boundary condition. And although there's really no complication in making it inhomogeneous, I'll start with a homogeneous version. And this one actually has an application, and inspired by a talk we had this morning. I'll mention applications only once in this talk. And that application is to Newtonian cooling. So if you have a Robin boundary condition, that's a model for a metal rod where one end is in a bath of liquid. Well, if the liquid is gradually corroding the end of the metal rod that's in the bath, then that coupling coefficient in the Robin condition is going to vary in time. Okay. So this is a classical problem as long as B is constant. It's a linear equation on an infinite spatial domain, so we ought to use a Fourier transform, right? But which Fourier transform? Well, if we were looking at a Dirichlet problem for the half-line heat equation, we'd want the sine transform. A Neumann problem, we want the cosine transform. And for a Robin problem, we want the Fourier B transform, also often known as the Fourier H transform. I'm calling it the B transform because my Robin coupling constant I'm calling B. Okay, well, just to remind anyone who might have forgotten, this is defined in terms of the cosine and sine transforms. You just want to take the proper reflection that's going to work well with this spatial differential operator. Here it is. It's just a linear combination of these two, and then it's got an inverse. And the point of this transform is that provided you're working on a space of functions that obey this boundary condition, it diagonalizes your differential operator. Okay? Exactly the same as the corresponding results for the Dirichlet and Neumann problems. Okay. So how does that work? To remind you, what you do is you apply the Fourier B transform to your PDE, and then you look at that, take out the spatial, turn the spatial derivative into multiplication by minus lambda squared using that diagonalization result, and then provided you're working with something that isn't too horribly rough, you can take your time derivative outside, and then you have an ODE, which you can solve, and then the initial value is just the Fourier B transform of the initial datum, and then you just apply the inverse Fourier B transform to this equation, and you end up with a result. Okay, So this is exploiting the diagonalization of the spatial differential operator by that Fourier B transform. Okay, so let's try that. Well, the problem is when we have our B depending on time, then our Fourier B transform depends on time, right? Because there's B's in here, and the inverse, of course, as well. But then that means that you can't take the time derivative out, right? Because it's going to interact with the transform itself. So this is no longer true, and then everything else is just falls apart. So we need a new approach, right? How are we going to get that new approach? Well, I suggest we use the Fokas transform method. I know that some people here are experts, and some people might not have seen this at all before. I'm going to try to median and give you some introduction to how it works without going through every detail. But to give a view of how it's been applied, I should mention it originated as a way of doing something like Ken was just talking about for problems on a boundary, right? So a half-line nonlinear Schrodinger equation, or a half-line KdV problem. And you end up formulating these Riemann-Hilbert problems and solving them using the techniques that we've just heard about. Well, for linear problems, it turned out that it actually yielded a lot of new results as well, and the method's much simpler. So I'll be able to give a little bit more indication of how it works. So here's just a very brief overview of some of the classes of problems to which it's been applied, without attempting to be at all encyclopedic of all of the particular problems that it's been applied to. But it's not just been applied to evolution equations, it's also been applied to nonlinear equations, elliptic equations, evolution equations in more than one spatial dimension, and plenty more. Okay, so it can be seen as a method for obtaining the transform pair that is tailored to a specific problem. Right, so that's the transform pair that diagonalizes the spatial differential operator. So it's a way of finding the Fourier sine transform, right? If you've got a Dirichlet problem for the heat equation, and similarly. But if it's a problem of higher spatial order, then what is the correct spatial transform to use? Well, the Fokas transform method tells you what the transform is. Okay, how does it work? I'll go into some details in a bit, but first to give you an overview. So the first stage of the method, you assume that there's a solution of the partial differential equation and the initial condition. We're not going to use the boundary conditions at all yet, just the PDE and the initial condition. And you derive a couple of equations that definitely Q must satisfy. The first is called the global relation, and that relates Fourier transforms of the solution and the initial datum with some kind of time transforms of the boundary values. So if it's the heat equation, then you're just going to have the Dirichlet and Neumann boundary values. Then you also derive the Ehrenpreis form, as it's called, which is a contour integral representation of the solution. And it, again, features these same things, right? The Fourier transform of the initial datum, and also these time transforms of the boundary values. Okay. So that's fine, except if we're thinking of the heat equation, then you're going to get two boundary values in there, and a well-posed problem can only specify at most one of them exactly, so you need to get rid of the other one. So we need to construct a data to unknown map, which I'm abbreviating cheekily to a DTN map. Yeah, so there's ways of doing that I'll explain later. But then after that, once you've achieved that, you have a representation of the solution, right? And more than that, you know the solution must obey exactly this equation. It's an explicit representation of the solution, so there's only one solution. You have unicity for free under the assumption of existence that you made at the beginning. Okay? So then in stage 3, which I won't have time to really talk about in this talk, but in stage 3, you take that result from stage 2, that formula, and you just pretend you don't know where it came from. It's just a formula defining a function, and you check whether it satisfies all of the criteria of your initial boundary value problem. Provided it does, you've got existence, and this bootstraps the method. Okay. Stage one. So we're going to just try applying the Fourier transform to the partial differential equation. Okay, but the Fourier, this is the wrong Fourier transform because our solution of our PDE doesn't exist for x negative. So this is nonsense. So we want to actually apply this Fourier transform, right? And that has the advantage that this integral makes sense for some complex values of lambda as well as just real values of lambda. But you pay for that by getting some boundary terms, right? When you try to derive the sort of diagonalization result, you do integration by parts and you find some boundary terms showing up. Now, that means we've picked the wrong transform, right? That means we should have used the sine transform or the cosine transform or whatever is correct. But humor me, and let me continue with this. The right-hand side of this is I'm going to pretend data. Okay? So that's still an ODE. It's an inhomogeneous ODE, but it's still really easy to solve. And here's the solution. Okay? So when you integrate that data, you get these two. These are, well, they look like some kind of time transform of the boundary values. Okay? They came from integrating the data, but they look like time transforms of the boundary values, so I'm going to call them that from now on. Okay. Right, so that equation is our global relation. It's valid for all lambda in the lower half plane. All right, well, this global relation relates the initial datum to the Fourier transform of the solution, that's the thing we want, and these boundary values. So let's make this the subject of the formula, and then apply the inverse Fourier transform, and there we go. There's a representation of the solution. Okay, but I'm going to do something else that now we're going to start applying. Now we're going to start using complex analysis. We're going to take this real integral, and we're going to say let's think of that as a contour integral along the real line, and we're going to deform it. We're going to deform it from the real line up into the upper half plane. I'm going to deform it like this. So for the purpose of this talk, don't worry about d minus. That's not going to be important. We're just looking at d plus. Okay? So we deform it as far as we can, and in order to justify that deformation, we just need to use Jordan's lemma and a nice simple asymptotic analysis of these f0 and f1. But then we're going to do a little more, and we see that we can actually replace these two terms evaluated at current time t with instead evaluated at final time capital T. And again, that's just another Jordan's lemma argument to show that you get decay of the difference as lambda goes to infinity from within d plus. Okay, so. Right, why I've done that is maybe not exactly clear at the moment, but hopefully it will become clear later. The idea is really what I'm going to do eventually is I'm going to show that some other terms that are going to end up inside this integral disappear using Jordan's lemma, but I can only use Jordan's lemma within d plus. I can't use it here, and I can't use it here, so that means I can't get rid of those terms unless I have earlier on, at this stage, deformed up into the complex plane. Okay? Right. So we have a global relation and an Ehrenpreis form. And the Ehrenpreis form is nice because it's a representation of the solution, but it's not effective because we've got both the time transforms of both boundary values here. And we can't have both of those specified in the well-posed problem. So we need to do stage 2. We need to construct our data to unknown map. So first I'll explain how to do this for an initial boundary value problem, right? A static problem with b a constant. Okay, so we'll look at the static Robin problem. Well, if you have take your boundary condition, b is constant, then you can apply this transform. Right? Apply this transform to both sides of this equation. It's linear, so it separates over the two, and you end up with this. Okay, and note that b is constant, so b comes out of the transform, and that's why it's multiplying here. Okay, so that's an equation, a linear equation linking f0 and f1. So if we can get another linear equation linking f0 and f1, we can solve and then substitute in, and we're good, right? Well, the global relation, remember, is valid in the lower half plane, and we have an integral that lies wholly in the upper half plane. So the global relation is no good unless we put the map lambda to minus lambda in there. Okay, so let's do that. And note that f0 and f1 depend on lambda only through lambda squared. So actually, they're unchanged by that map. There's no change of variables there. Sorry, the change of variables doesn't affect anything. Okay. So we now have two equations in f0 and f1. Two equations in two unknowns. Let's solve it. Well, not quite that simple. These are the two things that we want to know about. That's Fourier transform with initial datum, so we know that. This is the Fourier transform of the solution at final time. We certainly don't know that. But let's just sort of pretend we do. Solve the linear system. Plug it into the Aaron-Price form. Your f0 and f1 go in here. And then you can show that the terms involving, the terms that have this factor in them evaluate to 0. And again, that is a Jordan's lemma argument, and that's a Jordan's lemma argument that works provided you've already deformed the contour as far as you can earlier on. Okay. So I want to make the point that all static initial boundary value problems, constant coefficient linear evolution equations, no matter whether it's a half-line problem, a finite interval problem, a multi-point problem, a non-local problem, an interface problem, whatever it is, always you can do something like this. You might have a much larger linear system, but you can always do this, and provided it's a well-posed problem, you can always make step 2e work. Okay. So how does step 2e work? Well, the terms that involve this Fourier transform of the solution at final time all end up looking like this, where r is some rational function, and r always ends up being a function where the numerator is a polynomial of degree less than or equal to the denominator. Could be equal though. So we want to use Jordan's lemma. So we want to get some decay from this term, sorry, from this factor, I mean. So integrate by parts, and then Riemann-Lebesgue lemma will tell you that this one is order 1 at worst, so we get decay. And then this doesn't blow up, so you can use Jordan's lemma. Well, that doesn't necessarily tell you it's 0, because r might have some poles, right? So we have to make a modification, actually. When we were deforming our contour up into the upper half plane earlier, we should have been a bit more careful. We should have actually said, well, all of this stuff is analytic before we solve the linear system, right? Before we try to do our D to N map. It's all analytic, so we can deform over any finite region as much as we want. So let's pretend we did that. We deformed our sector outside a where are we? A disk of radius r. Okay. Well, we've chosen our disk so that all of the poles of our rational function are within the disk. Problem solved. Okay. So we need a little bit of notation now for this time transform. I've been talking about f0 and f1 as time transforms of the Dirichlet and Neumann boundary values, respectively. Well, I'm going to be applying it to some other functions, so I'm going to call it this this transform capital F. Okay. So F is just capital F is just the time transforms if you put the boundary values in there. All right. So how do we modify this approach for initial dynamic boundary value problems where our Robin coupling coefficient is allowed to depend on time. Well, the global relation is still fine. Okay. Now I'm actually not going to do the lambda to minus lambda map at this stage because it's going to turn out that I'm not going to solve. Oh, sorry, I should go back and make something a little clearer. So when we did this D2N map, we really weren't constructing the Dirichlet or Neumann boundary values, right? We were constructing the unknowns F0 and F1. Okay, this is why I'm not calling it a Dirichlet or Neumann map, because we're working fully in the spectral space, right? We're constructing F0 and F1 directly, okay, and that's why we're able to express it as a linear system rather than any kind of complicated integral equation, okay? So therefore, it was crucial to apply this lambda to minus lambda map in the global relation earlier on so that we get something that we could actually substitute into here on an equation that is talking about an integral in the upper half plane. Well, it's going to turn out that with initial dynamic boundary value problems, we can't do that. We can't work fully in the spectral space. We're going to actually have to construct the Dirichlet boundary value itself. And that means that I don't really care about making sure that this is valid in the upper half plane anymore, so I'm just going to leave it as it is for now. Okay? Right. Global relation is still fine, but then our other equation came from the boundary value. Sorry, I apologize, from the boundary condition, the Robin boundary condition. But now if we try to apply that transform, we can't take the b outside our transform anymore because b depends on the variable that we're integrating. So this is just false. So what happens when we apply the transform? Well, it's still linear, so we still get f1 coming out of this term. But from this term, we get this transform of b times the Dirichlet boundary value. All right. Well, now this together with this doesn't give us a linear system in our two unknowns, so we've got to do something else. But we can at least substitute this into the global relation to eliminate f1. Okay? And I want to eliminate f1 because remember this is the transform applied to the Dirichlet boundary value. So I've got Dirichlet boundary values appearing in both this and this. Okay? So when I do that, here's what we have. Okay? This is an integral equation for the Dirichlet boundary value. And that's known. And that's, of course, not known. But terms with this have a history of magically disappearing using Jordan's lemma. So let's hope that maybe we can pull such a trick again. Pretend this is known. All we need to do then is invert this integral operator, right? That's our task. Okay. Here is, this is the capital F transform, the time transform. E to the lambda squared s is this kernel, which looks a lot like a Fourier kernel, but it's got lambda squared where we want an I row. So let's put an I row there. Change variables. And remember this is integrating in time, so change variables, just a substitution. And sorry, I'm not sure if you can see this. I maybe made the gray too light. But what I'm trying to show is that in the lambda plane, in the lambda variable, we have our global relation that works, this equation that works in the lower half plane. So when we map it to the row variable, that is now the whole plane, except there's a cut along the negative imaginary axis. Okay, and this square root is the principal branch. All right. So do that, and we now, on the right-hand side, do have something that looks a lot more like a Fourier transform. The left, okay, this looks unpleasant, but it's known, and this looks even worse, but we're pretending we know it. So let's think about that right side. We can actually write this as a sum of two Fourier transforms, right? There's the Fourier transform of B times the Dirichlet boundary value, and the Fourier transform of the Dirichlet boundary value, except multiplied by the square root of minus I rho, and now I'm using this temporal Fourier transform. Okay? All right. Well, if that was minus I rho instead of square root minus I rho, I'd know what to do with it. Right? But it's not. It's square root of minus I rho, but maybe it's a half derivative. Maybe. So this is the point where you send your student to go and learn about fractional calculus. We found a book, and this is what we learned. So there's lots of ways of defining fractional differential operators. Really, really lots of ways. I'm going to talk about two. Well, 1.5 ways of doing it. It turns out that it tends to be easier to define a fractional integral first, and that's essentially because you have a guiding principle in the Cauchy's formula for repeated integration, right? So that you can write lots of integrals as just one integral. Sorry, lots of successive integrals as just one integral. So that suggests that maybe you should define a fractional integral of order positive real alpha like this. Actually, we're only going to care about alpha, a positive rational number, for what we're doing. But in principle, alpha can be any complex number, provided its real part is positive. This will still work. So if you do that, then it's not so hard to show that this fractional integral operator interacts with power functions in the way that you'd hope. Okay? And we're eventually, if you'll permit a spoiler, we're eventually going to be looking at a sort of fractional Frobenius method. So we want to be able to deal with fractional power series, and that's a good sign, right? That it's interacting with power functions in the right way. Okay. So we've got our fractional integral operator. Now we want to define a fractional derivative. So we can integrate as much as we want in a smooth way, whatever our alpha is, any positive real number. We can so far only differentiate positive integers, right? So if we want to differentiate some alpha, then you can combine that as differentiate a bit more than you need up to an integer, and then you integrate back. Okay? There's two ways of doing that. You either integrate and then differentiate, or you differentiate and then you integrate. Okay? So I'm not trying to claim that it's obvious that this is the right way to define a fractional differential operator. It's certainly not the only way that people have defined fractional differential operators. There's many, many ways, and some of them make a lot more sense in different settings. But these two ways seem to make sense given the particular problem. And it's worth noting that both of these differential operators interact with power functions in the way you'd expect, except the constant function, where the Caputo fractional derivative, that's the differentiate first then integrate operator, sends it to 0, and the Riemann-Liouville doesn't. So maybe that's a sign that the Caputo fractional derivative is the right one. We'll see. But yeah, something you can immediately say is they're definitely not the same. They're not equivalent. Okay, how do these interact with the Fourier transform? Well, if you take the Fourier transform of a fractional integral, then it does what you'd expect, right? You multiply by minus I rho to the minus alpha. And for fractional derivatives, again, it does what you'd expect. But bear in mind that we're thinking of our functions going to be defined only in our time interval from 0 to final time capital T. So that's A is 0 and B is capital T. I should have done that. And that means that you're going to end up with boundary terms from your Fourier transform, of course. And those boundary terms differ depending on whether you're looking at Riemann-Liouville or Caputo. Okay. So, whirlwind tour of the things we need from fractional calculus. We've learned that our motivating guess of maybe this thing is this thing for some definition of this was not quite right. There's going to be some boundary terms in there. But it was not a disaster, right? At least we got the square root of minus I rho in there. Okay. So we are working with this Fourier transform, and we're going to try and apply the inverse Fourier transform, and I do it in a slightly complicated way, which I won't go into for reasons of time. But we have, this is our equation, right? This is the equation we had before. Fourier transform initial datum, Fourier transform of something we're sort of pretending we know for the moment. This is something we know times the thing we seek, and this is Fourier transform of the thing we seek. Now, if we apply what we just learned about Fourier transforms of fractional derivatives, then we can turn this term, the square root of minus I rho times the Fourier transform, into this. It's the Fourier transform of the Caputo fractional derivative plus boundary terms. Of course, we could have done the Riemann-Liouville, but I'm going to show you the Caputo one. Okay, now we're going to apply this inverse Fourier transform. What do we get? And again, I'm regretting making the gray so light, but it doesn't matter too much because the reason I grade these is this term does evaluate to 0. Good news. And this term actually evaluates to 0 as well. So we're just left with Fourier inverse transform, Fourier transform. So that's just a Caputo fractional derivative. And this is just b times the Dirichlet boundary value. And this is data. And q of 0, 0, that's the solution evaluated at the 0, 0 corner. But that's just the initial datum evaluated at x equals 0. So we know that. And that's just a formula that you can calculate. OK. Yes?
So, but in this inverse Fourier transform, your parameter capital T is not involved.
Yeah. Okay. So this does depend on T. That's true. So it's sort of it's hiding in here. That's true, and it's hiding in here as well.
No, I mean T capital T.
Yes.
So if it were infinite, I would be very comfortable because with your function analysis as a function of rho upstairs, and of course this one will traduce it, but T is not only analytic, it is the entire function.
Well, this does depend on T.
Huh?
This does depend on T. And this also does depend on T.
Because I don't see how this inverse transform. So probably it depends on the domain of this inverse transform. Yeah, because it should be produced.
There's no capital T, right?
Yes, there is no capital
If
T.
you go higher, yeah, there. Where's capital T there?
No, this is what I'm asking.
Oh, sorry, I understand. Okay. So so this is valid only for.
No, yeah, the domain should be depends on.
So phi is a function on the closed interval 0t, right?
Yes,
So this inverse transform is only valid at little t in the closed interval. Sorry, in the open interval, I guess. 0 final time.
Just kind of Fourier transform applies to function defined only non-zero limit to 0.
Exactly. Yeah. So extend phi by 0 to the full line.
No, but Andrei, the Fourier transform itself, if T is fixed, vector T is entire function, correct? So I do inverse transform. Of course, to define it, I only need function psi to be well defined upstairs. But I want to get is sort of which is just has support on the interval theory, right? How can you see? So when it is just zero infinity, then of course if you take then domain is easily described. It is an analytic upstairs function. If you do your transform, I get function whose support is zero. So how should I describe function psi so that this Fourier transform would be on zero C?
But this results introduce this transform.
Sorry?
This results you introduce this transform. What do you say?
No, this is not. This is not new. Maybe we can talk about it more later. Okay. Okay. So let's rearrange that equation, and we have the Caputo fractional derivative of, I'm going to call this Dirichlet boundary value y from now on. So the Caputo fractional derivative minus, there's a variable coefficient here, and then this is all data. Okay. So let's try and solve it. We know the initial value, because the initial value is just the initial datum of the original initial dynamic boundary value problem evaluated at x equals 0. So why have we used the Caputo fractional derivative? Well, we used it because it made sure that we ended up with this term that we know, and this term disappeared, right? So we got the boundary terms that are easy to deal with. This is a nice sort of mirrored result where in the or not result, mirrored way of looking at things. So the Fokas transform method is a way of finding the right transform for your operator. Well, here we have the transform, and we want to find the right operator, the right fractional differential operator that interacts with that in the nice way. This is the way to do it. Okay, so let's try and solve this this fractional linear ordinary differential equation. Well, there's established theory of how to do this, which first appeared in a book from 2006. And if you assume that your coefficient and your inhomogeneity are both fractionally analytic, then there is a unique solution of the problem, and it's given by this fractional power series, and here are the coefficients using this recurrence relation. Okay, so what can we do with that? Well, supposing things are smooth, and supposing you have that fractional analyticity, then you can get your Ehrenpreis form, and here in the Ehrenpreis form I just used that boundary condition as well, that dynamic boundary condition, and plug in your Dirichlet boundary value that you've worked out by solving that fractional differential equation. Well, actually, let's plug in the partial sum of that and check that it converges nicely. Well, we find that firstly, there's a unique solution of the problem. Secondly, if you plug in the partial sum of your solution to the fractional initial value problem, then you get nice behavior of the integrals defining this. This QK satisfies the PDE and satisfies the initial condition, and if you take the limit as k goes to infinity, then uniformly your solution approaches the true solution. Okay. So that now completes stage 2. We've got an effective representation of the solution, and we've got a practical method for obtaining it to whatever precision we like. How does that work? Well, for unicity, we know that the assuming there exists a solution of the original problem, that means that that solution must satisfy the Ehrenpreis form, that's this equation, with this being the Dirichlet boundary value. And the Dirichlet boundary value must satisfy the Caputo fractional initial value problem. And then we have that result from Trujillo that says that the initial value problem has a unique solution, so we're done. The uniform convergence is a standard theory that I won't go into in too much detail. But then once you've got that, you can differentiate under the integrals, and you see that the x and t dependence in this formula is very, very simple. So the PDE follows immediately by differentiating under the integrals. And then if you plug in time t equals 0, then you see that this is just an inverse Fourier transform with the Fourier transform initial datum. So that's just the initial datum here. And this one, if t equals 0, then you can use Jordan's lemma to see that this whole integral evaluates to 0. Okay. So the new bit, the convergence, the uniform convergence result, uniform convergence in x and t as you take more and more terms in your fractional power series. Well, if there's a solution, it satisfies the Ehrenpreis form, and so you can subtract the solution q from the approximate solution. You see that you get the only thing that's left is this integral with a remainder, where that remainder is the tail in the fractional power series. Change variables, and you end up seeing that this remainder gets replaced by this other thing that is expressed in terms of the remainder. What is it? Well, it's the remainder plus, it turns out, a Riemann-Liouville fractional integral of b times the remainder. And then because you're working with the tail of a fractional power series, well, if you want to prove anything about fractional power series, you compose it with a power function, you get a power series. So it's actually really easy to prove things about this. So we get uniform convergence in 0t of b times rk, and then it turns out that the fractional integral of something that's uniformly convergent is also uniformly convergent. So rk converges uniformly in time. So now at x equals 0, this disappears, and we've just got an inverse Fourier transform of a Fourier transform of rk. So that's rk. So at x equals 0, we have uniform convergence of ek as k goes to infinity, to 0. And then for x positive, you need to do some real analysis, which I won't go into. Okay, so that's stage 2. For stage 3, we need to suppose all the criteria of the previous theorem, except we're not going to suppose that there exists a solution yet. Okay, so we're just going to have our solution representation, qk, and you can show that in the limit, uniformly in t, it satisfies the boundary condition. So we really do have a solution of the initial dynamic boundary value problem, and it is being approximated in the right kind of way. So that's stage 3. And I won't go into the proof of that because it uses some pretty similar techniques to the proof I just sketched. You just have to start it in a slightly different way. Okay, so to conclude, this was the overview I gave you before for initial boundary value problems. What have we had to do differently for initial dynamic boundary value problems? Stage 1, you had to construct that global relation in Ehrenpreis form. Remember, it used the partial differential equation and twice, apparently, sorry about that, and the initial condition. But it didn't use the boundary conditions, so it's the same. We haven't had to modify that at all. Stage 2, we had to do something different. We couldn't work in the spectral space anymore. We had to actually construct the Dirichlet boundary value explicitly, and we had to do it using a Caputo fractional differential equation. And then we also had to come up with a convergence result, because we can only solve that approximately, at least to my knowledge of fractional differential equations with variable coefficients. The best we can do is this fractional Frobenius method. And then for stage 3, which I didn't tell you how it works in the static case, but the argument is very, very different there, and it's a bit simpler. Here we had to do a bit more work, and also we needed another convergence result. Okay, well, I've been talking about the heat equation. I advertised linear evolution equations. You can do this with the Schrodinger equation as well. This is free space Schrodinger equation, constant coefficient. So you can have your you can have a inhomogeneity in your boundary condition. That's fine. That really makes very little difference, except you now have that inhomogeneity appearing in your Ehrenpreis form, and it appears in also the right-hand side of your slightly modified Caputo fractional initial value problem. But you can still solve it, and this is what you get. Under the same criteria, you get the same kind of approximation results, except we only got them pointwise in X for linear Schrodinger, and I can't tell you whether that is a fundamental restriction or just we weren't able to do it. Linearized KdV, so this is now a third order in space equation, slightly different dynamic boundary condition. Here's the solution. Okay. Now, note here, we've only got one boundary condition, and if we took our when we take our Ehrenpreis form, we're going to have 3 boundary terms, right, from that integration by parts in the when we're trying to diagonalize the differential operator. So we've only got one boundary condition to get rid of one of them, but we can use 2 copies of the global relation under 2 different cube root changes of variables, and that's why. And then you have to eliminate the Neumann term, and that's why you end up with a more complicated formula here. But then you get a 2/3 fractional Caputo initial value problem with a more complicated right-hand side, but still you can solve it. Assuming you're working with fractionally, I guess it's now 2/3 analytic functions, and you get the same kinds of convergence. Now, I hope you'll forgive me for not writing these theorems out in full. They don't really fit on a slide. Well, then we could do linearized KdV if we take the opposite time direction. You now need 2 boundary conditions for a well-posed problem, at least in the static case, and it turns out it's the same in the dynamic case. And now here's the solution representation. We now have a very different type of equation, right? Because here we have the Caputo 1/3 derivative, and this is not the Caputo 2/3 derivative, because it turns out that the theory of such equations is pretty unpleasant. In fact, I believe open. But here we've chosen, we've elected the sequential twice 1/3 Caputo derivative. Okay, so this is a statement that while this is true, when you try to put that into a fractional version, it's false. So we need to pick the right fractional differential operator again. But it turns out this is the one that works, or at least it's a one that works. And again, there's theory for these that tells you the fractional initial value problem has a unique solution, and here it is. And again, you get the same kinds of conversions. Finally, the general problem. the general problem, you end up with, again, so now it's a system of fractional initial value problems. A system, well, there's n minus n of them, right, for each of these values of k. But then there's n of your boundary conditions. So put them all together and you get a system of n equations and n unknowns. Each of your yj's is a boundary value of a different order. I don't know whether you can solve that. I don't know whether the solution is unique. As far as I know, no one knows that in general. I mean, of course, if these were not linear independent, you'd be in trouble. But I don't think there's even a sort of constructive version. Sorry, I don't think there's a positive result even. But if you assume that if you can plug in someone else's result, that there is a unique solution of that system, then the initial dynamic boundary value problem has a unique solution. And if the solutions are 1/nth power series, then you get the same kinds of convergence results. OK, so very briefly, I will mention a few possible extensions to this work. So the well-posedness for those general problems is going to require a general theory for systems of variable coefficient sequential Caputo fractional differential equations, which at least I don't know, I think is not known. After that, it should be relatively easy to decide well-posedness for any dynamic boundary conditions. But there's some subtlety to this, because you might have dynamic boundary conditions that are like almost everywhere linearly independent, but then at some particular time they become linearly dependent. Does that break well-posedness? I don't know. So we only worked with ordinary points of these fractional initial value problems. You can do regular fractional singular points as well, using these same results in this Dirichlet book. We didn't do that, but it should be possible. You'll get some different convergence in your solution of your whole problem. Equations with spatially lower order terms, that should be fine. We didn't do it because this is already notationally unpleasant enough without that extra complication. How about finite interval problems? Well, they're more complicated because when you go through this approach, you don't get a fractional differential equation of any kind. You get some kind of more complicated pseudo-differential equation. Now, that doesn't mean we can't do it. There's some small progress that we're making with Francois Monard at the moment, but not ready to talk about yet. If you try and do this for multi-point, non-local interface problems or problems with higher spatial dimension or nonlinear problems, then that's going to be at least as hard as the finite interval problem, and some of them introduce more significant difficulties of their own. So that's for further in the future. But then some spectral theoretic view might be interesting because the Fokas transform method, as I've said a couple of times, can be viewed as the way to derive the differential operator that diagonalizes the spatial. Sorry, the way to derive the transform that diagonalizes the spatial differential operator, right? Well, here our spatial differential operator has domain that varies in time. So its spectrum is varying in time. So how does that interact with this method? What are we learning about the spectrum from this, the fact that this works? I don't know. Thanks very much.
Questions, please?
Yes?
If you have the right-hand side, what class will it have to be in order to make it work?
The right-hand side of the PDE. I don't know, but There are works by Dionysios Mansavinos and Alex Himonas that would be the place to start for that. As far as I know, they have looked at nonlinear Schrödinger with Dirichlet boundary condition on the half-line and KdV with Dirichlet boundary condition on the half-line. I think there might be a couple more recent than those. But they certainly haven't studied dynamic boundary conditions like this. But they were able to get some well-posedness results for the nonlinear Schrödinger out of using exactly the method that you're suggesting. Yeah.
So in your fractional function equation, you showed how you could actually solve it. What happens if it's based on a series? What is the limitations for the convergence of that series? Does it converge for all time, or does your method start to fail?
So we assume. Hold on. Let me go back to the statement.
To the big picture, or is it just run before you solve it? If you go back before that, you're based on the exact solution without some of these sub-Ks, right? There you go.
Yes.
Most BFT is that.
Yeah, so we assume that both of these converge as fractional power series on some interval where r is strictly greater than final time.
For those two equations in general, can they then develop spontaneous other singularities, or you just don't care because you're assuming you're okay and you care about?
That was the approach I took. I don't know the answer in general.
You want B as a function of t, as a function of x. Is there any difference? What's secret about this?
So B is the coefficient in the boundary condition. So I don't think it.
Yeah, if you consider those boundary conditions, maybe for more general problems and talk high order derivatives, but we have included as x.
B is a function of x. So that's like a.
Oh yeah, then
I mean, I guess you could have at different times you could have different boundary conditions, and some of them are maybe multi-point conditions. But then you sort of stitch it, do for some finite time, and then stitch forward. Yeah.
So for B of t as an exponential function, exponentially decaying, so there is possibility to have exact solution without any recurrent solutions. So you didn't compare your solution with anything that can be another way.
Did not. Should have done. Thank you. Good suggestion.
But similar question. In some situation, we have this, that you assume that B is expanding this fractional power. So when it is k over 2, then the usual homomorphic function is included. But if it is t to the 2k over 3,
Mm-hmm.
it means that there is no homomorphic just with respect to t.
Correct. Yes.
You also mentioned that one of the problems may happen that if you have a system of these boundary conditions and they would degenerate at some time, then you don't know what to do. But you already had two conditions. Have you checked on this at this point?
Yeah. Didn't, because sorry, I'll go forwards to where that problem is written out. Where is it? Yes, this problem. Well, those ones don't ever have that case happening. So, yeah, that was the example. But it did occur to me this morning as I was putting the finishing touches that is something we should have done. Yes. Thank you. Good suggestion.
Is there any chance to do long time asymptotics for some of those linear problems?
If you wanted to do that, then you would need your fractional power series to be accurate representations to be convergent for all time, which maybe is something you're willing to accept. And in that case, yeah, that should be something you could do. Yes. Yeah, absolutely. You would need to know how B behaves. But I mean, B is known, right? So I'm assuming B is a...
Convergence is not good enough. That's what I'm saying.
Yeah, you're absolutely right. Yeah. So, okay, I guess I'm not so scared of B as I am of G, right? I'm more worried about whether you've got nice convergence of this function, right? Because this is a inverse Fourier transform of a Fourier transform evaluated at something weird, right? A priori, it's not immediately clear that that is going to be nice for large time. Maybe it is sometimes, but...
Any more questions? Just quickly add, basically adding to previous question, comment, I think if it would be some explicitly some form of solution, a comparison to some, what you could calculate explicitly, some numerical solution would be more add to convincing of this technique. Okay, let's thank everybody.
Thank you.